thing or two about. And one of them is I can tell you a little bit about where the synchrotron light comes from, how the X-rays are produced, and how, like, what all of the technology is behind the scenes that generate and deliver the X-rays to the beamline so that protein crystallography and all kinds of other experiments can be done at the light source. So here's the big picture from up in a helicopter of the building that the light source is in. You can get a sense of the scale of this building by seeing the cars in the parking lot. Right, this is a really big building. It's the business part, the part that generates the X-rays, is sort of at the inner part of this circle and has a circumference of just under 800 meters. The hallway around the periphery of the building is about a kilometer long. So it's a really big building. The facility, the whole purpose of this enormous building is to make light, to make X-rays. For some experiments, UV or IR light, but for most of the experiments, X-rays of various energy ranges. And the thing I'm going to talk to you about today is how this big machine makes light. So let's start off by talking a little bit about this funny word that I've now just used several times. So when you talk to a synchrotron guy like me, we use the word light in a way that's a little bit different from how the word light is used in normal conversation. In normal language, the word light refers to a very small fraction of the whole electromagnetic spectrum. Just a little swath right here in the middle that's called visible light, the things that our eyes are able to detect. To a physicist, light refers to any kind of electromagnetic radiation. The thing that distinguishes the different kinds of electromagnetic radiation is the wavelength of the light. So light has this wave nature and it has some length associated with it. And the different lengths of light are used for different purposes. And the way that you can understand that is sort of, what's on the scale of the light that you're talking about. So if you talk about things like radio waves, which is how radar works, well, we use radar to look at clouds or boats on the ocean or airplanes or geographical features, geological features. So things that are on the scale of tens or hundreds of or thousands of meters in size. And the reason that we use radio waves, the reason we use radar for that is because the wavelength of the radar is more or less the same size as the wavelength of these big features that you can measure with radar. Similarly, when we look through a microscope and we use visible light to look at things like, well, as the graphic suggests, we look at protozoans, little things that you can see in a microscope. The reason why the microscope works is because the wavelength of the light and the size of the features that we're looking at through the microscope are about the same size. So light in the visible range is the right scale. It's the right kind of ruler to use to measure the things that we can see in the microscope. So why do we want a big facility that measures X-rays? Well, the thing that we do at the big facility that measures X-rays is we do various techniques to understand how atoms stack together to make things. In the context of protein crystallography, you're looking at how carbons and oxygens and nitrogens and a few other things link together in chains to make proteins. Well, atoms are of a certain size, about an angstrom, about 1 part in 10 billion of a meter, 10 to the minus 10 meters. The distances between atoms in a protein or really anything else is on the scale of angstroms. X-rays have a wavelength that's on the scale of angstroms. So X-rays are exactly the right kind of ruler to understand how angstrom-sized objects stack up with distances on the scale of angstroms between them. X-rays are the correct ruler for the job. We do protein crystallography with X-rays for that reason. So we need a source that makes a lot of X-rays so that we can do those experiments. Now, just to sort of understand the context of that big building I showed you a second ago, it's useful to think about who visits the synchrotron. And the answer, the sort of broad answer is, well, anybody who has a question that's answered by using X-ray. So if you have questions about how atoms stack together, how electrons interact with atoms, things like that, well, X-rays are just the right tool for the job. So on the left side of this slide, I show sort of comically who those people are. They're professors and students. That's a large portion of our population of visitors at the facility are university professors and their students and graduate students or postdocs who come and do a portion of their work. We see a lot of industrial scientists, and we see a lot of people who, like myself, are government researchers. And then on the right side of this graphic, I sort of displayed a whole bunch of topics that we study at the synchrotron in this sort of descending spiral to sort of give a sense of the scope and depth of what we do. Basically, any problem for which you have a question that is well solved by X-rays, that's the sort of thing that people come and do. And so we get people who come and look at pharmaceuticals, and I think I have crystallography somewhere in this thing. But also lots of other issues. We get environmental scientists and people who look at materials and batteries and chemical processes, and the list goes on and on. We do a lot of different kinds of work with the synchrotron. But the question here today is not about the specific kinds of measurements or all of the fields of science. The thing I'm going to present to you today is just how does this machine work? How is this big building a tool that makes X-rays? Well, the story is pretty cool, and it's got a lot of parts. So we're going to go through each of the parts sort of step by step. What I have, this little icon thing that I've drawn here is sort of a simplified representation of what's inside of this big building. And there are, it turns out, sort of 5 basic parts of this building. And I'm going to go through this page really quickly and then back up and go through each of these lines individually, hopefully so that the whole picture makes sense to all of you. So inside of that big building, inside of NSLS2, there's a linear accelerator somewhere in the infield. It's actually sort of underneath this grassy area right here. There's a linear accelerator that generates an electron beam. That electron beam goes into a thing called a booster ring, which raises the energy of the electrons in that beam to well over 99% of the speed of light. So remarkably fast. Then there's a transfer line that transfers these very fast moving electrons from the booster ring into the storage ring. The storage ring is the part of this machine that actually generates the X-rays and other kinds of light that we use for the experiments. Those X-rays are channeled down beam lines that are all around the ring into all of the experimental apparatus. So that's the big, view from the same place as that photograph, view from like 100 feet up above. That's the big view of how the machine works. Now let's drill down and try and understand each part. So let's start with the linear accelerator. So here's a photo. I actually don't have a photo of the linear accelerator at our facility, and I've never actually been in that building, so I've not seen it myself. I've seen linear accelerators at other facilities. Here's one at a synchrotron that is in Canada, in the city of Saskatoon in Saskatchewan in Canada. It's sort of due north of Montana, out in the middle of the prairie. There's a city that has a synchrotron in it. And this is what their linear accelerator looks like. And you see that it's basically a big long tube that's on its side. There's like a power cable coming in, and somewhere way down here in the distance is the entrance to the booster ring. So what goes on in this blue thing is somehow the electrons are generated and accelerated down that line so that they can go off to the next part of the machine. Well, how does this thing work? Um, I don't they don't all work quite the same. So over here, I've got a little schematic that tries to explain how the electron gun that we have here at NSLS2 works. And the way it works is there's a little piece of metal. It actually could be almost any metal. I believe what they use here is the metal magnesium. Um, the metal is a target. It's hit by a laser beam, and the laser is used to heat up the magnesium. Eventually, as it heats up, the electrons, some of the electrons in the magnesium, get enough energy that they can actually leave the surface of the magnesium and go out into the vacuum that's on the outside of this piece of magnesium. This whole thing that I'm drawing schematically is, of course, in a vacuum vessel, so there's no air in there. The electrons can sort of boil off of the surface of the magnesium. Now, if that was it, the electrons would just sort of hover around the surface of the magnesium and then eventually fall back in. But what the clever thing that they do is they put these interestingly shaped pieces of metal in the vicinity of the magnesium that are charged either positively or negatively, that they make electric field lines that are sort of in a very special arrangement. So there's this sort of cloud of electrons here that get attracted by these two positively charged pieces of metal. They get accelerated, so they get some speed and start getting channeled down this beam path. Then over here, there are negatively charged things to keep those electrons sort of on the straight and narrow, right? The electrons then now have some speed going through these two negative plates that are repelling the electrons from both sides so that they stay, on the straight and narrow. So now using this laser that boils electrons off of the magnesium, and then this clever arrangement of charged plates, they get a beam of electrons that are all going in the straight line. So the part that boils the electrons off is maybe in the foreground. All of this other business is maybe here a little bit deeper into the picture. And now we have a beam of electrons that's heading in a well-known, a carefully calibrated direction. So what comes next? Well, coming off of the electron gun, the electrons don't have very much energy. The energy of the electrons, which is more or less the speed of the electron, the language gets a little bit more complicated when you start thinking about relativistic effects, which are important here because the electrons will be accelerated up very close to the speed of light. But to a first stab, the important thing is how fast are the electrons going? And the answer coming out of the gun is not very fast. So they have to be accelerated in a fairly short distance, right? This is maybe a few meters of length going into this picture. And over those few meters, the electrons need to be sped up very fast. And so they go into a device called a linear accelerator. And the business part of a linear accelerator is a thing that's called an RF cavity, which I've drawn schematically here. Here's a photograph of what an RF cavity looks like. This is a very old one from a very old accelerator. It's a little bit smaller than what's used in modern facilities, but it's basically the same thing. So this object is turned on its side from how this photograph is. It's turned on its side, and there's a bunch of those along the length of this blue gun thing. And the way it works is the beam of electrons enters into the first cavity of this funny device. And this funny device is sort of like a stack of donuts. The electron beam is going to go through the middle of it. As the electrons enter the thing, the charge on this RF cavity device is such that the electric field in the first cavity, the first donut part of the thing, the electric field is pointed in the direction that we want the electrons to go. But because charge has to be balanced through this whole device, it means that the electric field in the next cavity, the next donut section, has to be pointed in the other direction. This is a problem because the electrons will go through the first cavity and get accelerated, but then they'll sort of hit a wall in the second cavity because the electric field is pointed in the other direction. And instead of speeding the electrons up, it will want to slow the electrons down. So the trick here is to put an alternating signal on this device so that as the electrons pass through this device, the electric fields keep switching direction. So as the electrons are passing through this cavity, they get accelerated forward by the first cavity. In the time that it takes them to pass through this little connector, all of the electric vectors are turned in the other direction. So now as the electrons enter the second cavity, this blue arrow pointing that way is actually a red arrow pointing that way and pushes the electrons forward a little bit faster. Then they have to switch back when the electrons get to this cavity, and switch back again and back and forth and back and forth. So as the electrons pass through each of these areas of the RF cavity, they get pushed forward a little bit faster, a little bit faster, a little bit faster. The electrons leave the linear accelerator very close to the speed of light, which is awfully fast, but not fast enough. The energy of these electrons is well below what we need in the storage ring part of the synchrotron to do the work of the synchrotron. So the next part after the linear accelerator is the booster ring. The electrons enter the booster ring at a certain energy, a certain speed, and they leave much, much faster, much, much higher energy. The booster ring raises the electrons up to the energy that's needed to actually run the facility. So how does that work? The way I'm going to explain this is kind of fun. I'm going to show you a little video now of, and this seems like I'm doing something silly, but this is actually the best explanation of how a booster ring at a synchrotron works that I've ever seen. Absolutely the best explanation. So I'm going to start and show about 40 seconds of this video.
The accelerator.
So
Starting accelerator.
there we go. What you're seeing here is the Lego equivalent of the linear accelerator, putting the electrons into the booster ring. Watch the ball every time it goes through this house. It goes a little bit faster, 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 a little bit faster. Finally, after it goes through that little house often enough, that ball is going as fast as it's going to go. So let's break this down. What's really going on here? The thing that's inside of the little house in the Lego model are these two counter-rotating wheels that are spinning, spinning, spinning. And every time the ball goes through, the spinning wheels impart a little bit of momentum onto the ball, and it goes a little bit faster. This is the analog of one of those RF cavities that I just showed you. So in the booster ring has a whole bunch of these RF cavities around the ring, each of which serves the purpose of these counter-rotating wheels. That is, the RF cavity, every time the electrons go through the RF cavity, they get a little bit faster, a little bit faster, a little bit faster. Because they're going around in a circle, we can go through the RF cavities multiple times. And so by making a bunch of revolutions around the booster ring, those electrons are brought up to the full energy of the operating facility. From there, okay, so now, yes, now they have enough energy that they're ready for work. So now we have a transfer line that whenever we need to put electrons into the storage ring, we have a stock of electrons that are at the correct energy rotating around in the booster ring. So we can just sort of open the valve and inject some of these electrons from the booster ring into the storage ring. The way the facility works, actually, at the beginning of operations, we run the booster ring and fill up the empty storage ring. But in normal operations, we actually run in top-off mode. And over time, the number of electrons in the storage ring goes down. Some of the electrons just get lost through normal operations. And we can do top-off mode. That is, every couple of minutes, we let a little bit of charge from the booster ring into the storage ring so that the amount of current in the storage ring stays pretty close to constant throughout the course of the day. And what's really amazing then is that we have, you know, these machines and the electronics to control these machines that are able to do that very precisely and keep the amount of charge everywhere around the ring pretty constant throughout the day. All right, so now, once we have electrons in the storage ring, we have a couple of things that we need to worry about. The first thing we need to worry about is the fundamental problem with electrons, which is that electrons are negatively charged. And as these bunches of electrons are traveling along in the storage ring, they're going to push themselves apart. So what gets injected into the storage ring are these tight, tiny little bunches of electrons that then travel around and, using the tools that I'm going to show you in a few slides, generate the X-rays. But the problem with a tiny bunch of electrons is that as it travels along, the electrons are going to push each other apart and get bigger and bigger, kind of like I'm drawing here. But the applications that we have at the synchrotron, we want these bunches to stay nice and small so that the source of X-rays is as small as possible. That turns out to be very advantageous, particularly for experiments like protein crystallography, to have really small bunches. One of the things that gives us very good resolution in space for where all the atoms in the protein are the fact that the source of X-rays is very small. So we need to do something to keep the source of X-rays small. The way that's done is through a combination of what are called quadrupole magnets and sextupole magnets. And I'm showing you these pictures that I'm showing you here are unused devices that are sitting in the lobby of the light source so that you can actually go up and look at them. What you're looking at is a metal frame, a steel frame, with 4 magnets in it, 4 electromagnets. These are kind of like extremely powerful bar magnets. So a couple of them are north poles and a couple of them are south poles. So we have field lines that going through the center of this that look kind of like this schematic. And the electrons go right down the center of this picture. Now, the reason why we want to send the electron bunches through the quadrupole is because it helps to compensate for the bunch getting bigger. If you do the math on how the electrons interact with this kind of magnetic field, it turns out that this magnetic field will push the bunches in the directions that are not the direction of travel. So if the bunch is going like this into the quadrupole and it's expanding in all directions, this field will push in the 2 lateral directions. But the problem with the quadrupole is that it will stretch the bunch out in the direction of travel. So the quadrupole has done half of the job. It's kept the beam small in the direction perpendicular to travel, but the beam gets really big in the direction of travel. The sextupole has this arrangement of north and south poles and these kinds of field lines. And it does a very similar thing in the lateral directions. It helps keep the beam really small. And it also stretches the beam out in the direction of travel, but the other way. So the quadrupole stretches the bunch of electrons out like this. The sextupole stretches the bunches of electrons out like this in the opposite sense. So if you go through first the quadrupole, which stretches out one way, and then the sextupole, which stretches out the other way, going through them sequentially keeps the bunches nice and tiny in the direction of travel. So by going through pairs of quadrupoles and sextupoles, a bunch that goes in comes out a little bit smaller going out. It will expand again and then go through the next set of focusing magnets. It turns out there's something like 120 sets of these magnets all the way around the ring. So they're, as the electrons go around the ring, they're constantly going through these magnets that scrunch the bunches back down, and they help keep the bunches nice and small. Now, the next problem we have with this thing being a ring is that if any of you have taken physics in high school, you know from Newton's law that an object in motion stays in motion, that something is just going to keep going forward unless you act upon it. So those bunches of electrons want to just keep going in a straight line, but that building I showed you up at the beginning of the talk is a big circle. Well, turns out the accelerator complex, the accelerator machine, the storage ring, isn't really a circle. It's a 30-sided polygon. It's not a ring, but a bunch of straight sections and corners. 30 straight sections and 30 corners. What's at the corners? The corners are the magic thing that keeps those bunches of electrons going around the ring. That is, in the Newton's law sense, that something will stay in motion unless acted upon. The magnets in the corners are the things that act upon the bunches. They're basically like a big horseshoe magnet with a north pole at the top and a south pole at the bottom. This blue object that you see here, compared to me standing up, comes up to about here. And the length of that thing is more than 2 meters. This is a really big object. And it's bent a little bit, kind of like this picture over here. So the electrons are acted upon by the magnetic field in the bend magnet, which exerts a force inward and has the electron bunch turn through the corner. There are, it turns out, 60 of these around the ring, each of which deflects the electron beam through 6 degrees, so that as you go through 60 of them, you go all the way around the circle. The bend magnets produce X-rays. If you act upon charged particles like the electrons will lose energy and radiate a little bit. But the bend magnets produce rather feeble X-rays. What we use at most of the beamlines in the facility are insertion devices, and certainly at all of the MX beamlines at the facility, we use insertion devices. They come in 2 flavors that have just a sort of a subtle engineering difference between them that are called wigglers and undulators. The MX beamlines are all on the undulator kind of machine. And the way that works is shown schematically here. This is a photo of one of the wiggler devices in the storage ring. All of these striations that you see here are very powerful magnets. You know, the kind of like hard neodymium boron iron magnets that if you put it on the refrigerator, they're really hard to take off of the refrigerator, those really powerful ones. That's what this material is. They're those ridiculously powerful magnets, and they're pieces that are about this big. And then they're stacked up next to each other, north-south, alternating all the way down, alternating in this direction. And if there's one with a north pointing down, there's one underneath it with a south pointing up. So there's, you know, many of those powerful magnets. Each one of those striations interacts with the X-ray beam in the same way as the bend magnet, as this huge magnet, but in a very small area. So as the electron beam goes through this sequence of magnets, it wiggles back and forth, kind of like how I show here. And every time it goes past one of those pairs of magnets, it radiates a bit of light. So basically, every one of these striations produces X-rays more or less of the same intensity as this huge object, but all done in a very small space. The difference between and so in a wiggler, then you have all of these things that just sort of add up simply. So if this object has 100 poles, it's 100 times the flux of the bend magnet. The undulators have a little bit of special engineering in them, so that each of the poles of the device add up in a constructive way, in the sense of waves adding up constructively in phase. And you get these huge enhancements at special energies. And you can control at what energy you see the enhancement by changing the separation. So closing those jaws up and down to exactly the right spacing, you can move these peaks of enhanced flux of photons. You can put them at just the energy that you want. The point of using these undulators is that they're very highly brilliant, which is a funny term. Brilliance is this strange unit that physicists use to characterize the light at the facility. The most one part of it is flux, so number of photons per second coming down the beam line. But it also considers the extent to which the X-rays are like a laser, in that it's a non-divergent. So, if you hold a flashlight up to a wall, it will make a spot that's the size of the flashlight. But as you pull the flashlight back, that spot gets bigger and bigger. Yeah. But if you hold a laser pointer up to the wall and pull the laser pointer back, the spot does not get a lot bigger as you pull it back. We want that property in the X-rays, and we call that divergence or low divergence. An undulator has very little divergence. So if where the X-rays are generated, you have all those photons in a spot, down at the experiment, you have all those photons in the same spot. All of this together really is what helps make the MX beamline do what it does. Just to quickly go through the last little bit, we're now getting into the part of the experiment. At every beamline, there's a hole in this concrete wall. On the other side of the concrete wall is one of these insertion devices that generates X-rays. We can build a beamline by putting beam pipe up against that hole in the wall and carry the X-rays down to the instrumentation of the beamline that lets us do the kind of experiment that we want to do. Here's sort of the big picture of what this looks like out on the floor. The hole in the wall is way up here. The experiment is way down here. The distance from here to here is maybe like 20 meters or 30 meters. And the distance from here up into the storage ring where the X-rays are generated is maybe another 20 meters. So the whole length of the instrument that the scientist goes to is this big 50-meter long thing that produces just the kind of X-rays that you need for the experiment that you want to do. So I want to just end by saying again that we get all different kinds of people coming to the synchrotron. And what I really want to end with is a really important point for all of you, which is through programs like the Spark program, through faculty members you might work with when you go off to college, or if you go off to grad school after that, you might get opportunities to come visit us. What I'm showing you here are pictures of high school and college students who came to the facility with one of two friends of mine, Scott Calvin or Alessandro Larry, who teach at colleges in the New York area. That's Allie right there. Scott is not in any of these pictures. This woman right here was a beamline scientist many years ago at one of the beamlines, but everyone else you see here is a high school student or a college student. So just as you have the opportunity to participate in this Spark program, you might, as time goes by, find opportunities to work with the sorts of scientists who come to the facility. And so I'm really sad that I don't get to give this lecture in person because I don't get to meet all of you, but I am hopeful that I might see all of you or some of you someday at the facility because we love getting students at the Beamlines, and that's how we teach the next generation of scientists, the next generation of my colleagues. So hopefully I'll get to meet some of you someday if you get an opportunity to come to the facility. So yeah, thank you for your time. Thank you for your attention.
Thank you so much, Bruce.
Yeah. Oh, it's always a pleasure to join you. Thank you for having me.
Are there any questions? I have a few questions, but I want to see if anybody else has questions first.
Yeah, but please. Well, why don't you get us started?
Sure. How many beam lines are at the light source? I know you mentioned there were those 60. There were 60 different bending magnets. Is that where the beam lines are located?
Most of the beam lines are coming off of the insertion devices, which are in the straight sections, because those are the really specialty devices for producing X-rays. Although we do have some beam lines that are built for specific reasons on the bend magnet ports also. My beam line, for example, is built on a bend magnet port. We currently have 28 beam lines. We have capacity for something like 58 beam lines at the facility. So we still have room to grow. And there's a really important point there that I want to emphasize, which is we have 28 beam lines that are operating right now, and they all operate at the same time, right? Because they're all built off of the storage ring. The X-rays are going around the storage ring and generating X-rays everywhere that they go. So all 28 of these beam lines operate all at the same time. There's just this whole world of science going on at the facility at any hour of the day that things are operating.
And it's my understanding that the beam lines operate, some of them operate 24 hours a day. So is that correct?
Yeah. Absolutely. The time is precious. These folks who get like my friends Scott and Allie that I showed you just a second ago, they get maybe 2 or 3 days, and they have this whole laundry list of science that they need to get done in 2 or 3 days. So either through people being at the beam line or through automation of the instrumentation, we try and use every minute of the day because, the minutes are precious to these people who are coming for a limited amount of time. So yeah, we keep busy.
Wow.
Yeah.
Oh, we have a question that just came up. What was the difference between the undulator and the wiggler?
I didn't get to explain that in great detail because I was trying to sort of stay on time. I'm eating a lot into your hour here, unfortunately. So at a certain level, this is a great question. Thank you for asking this. At a certain level, they're almost the same in that they are arrangements of north and south directed magnets that switch as you go down the line. The difference is that the undulators are held to a different standard of engineering precision so that you can get, a wiggler is basically every one of those poles produces light in the same way that the bend magnet does. If you have 50 or 100 poles, you get 50 or 100 times more light because they add up in the simplest way. The undulators have a different engineering specification that's much more precise in certain ways so that you take advantage of the wave nature of the light and the light that's coming from each of the poles, then the waves of light come out completely in phase at certain energies so that you get this huge enhancement of the number of photons that are coming out of the device at specific energies. A wiggler, on the other hand, is a broadband source and generates light at all energies. The undulator generates light only at specific energies that can be changed, but only at specific energies. And so they're used for different kinds of experiments. Great question. Thank you.
Great. Excellent. Are there any other questions from our students or even from our teachers? Going once, going twice.
Yeah, I mean,
I think we're good.
I think that's fine. You've got
Yeah.
some other things to do today.
Okay.
I kind of blew through that, but hopefully that was fun for
That
everyone.
was great. I love the Lego demo. I remember that from last summer. That was that
So
makes it.
I keep Lego at my Beamline partly for fun, but I actually also use Lego to build little one-off sample holders when somebody brings something that's a funny shape. And I don't have time to go to the machine shop and get something proper made. I just make a little thing out of Legos. And
That's great.
Put it in and make measurements.
That is so
I'm a big
great.
fan of Lego.
Me too.
Yeah, I mean, Lego is science.
Yeah.
If you ask me.
Absolutely. Yep. That's great. Bruce, thank you so much for being here with us. I really appreciate it. And I hope one day we can be at a Beamline and we can meet you in person and be at the light source. Yeah, definitely fingers crossed on that.
I sure hope so.
Great.
Yeah, no, thank you, everybody. And Robert, thank you again and Aleda, thank you for the invitation. It's always a joy to join you. All right.
You're welcome.
Bye,
Thank you. Bye. Thank you. All right, everyone. So we have about 10 minutes left on our Google Meet. And if Google runs out, I have a backup plan. I created another link so we could just wrap up. I don't foresee us going longer than maybe 10 minutes after 11. So I know I'm big on staying on, on our time schedule and everything. But Bruce's talk, I think, was important for us to see. And I like the animations and everything that he uses. He does a much better job of explaining it than I think any of us could. So what I'd like to do is turn it over to John now so we can just take a quick look at that PDB report and just go over a few things with that so that students understand the reason why we had you guys do this little exercise, which is really a valuable tool for us. So, John, if you're ready, you can jump on and take over that. Is John there? Or did we lose him? Let me see.
Can you guys hear me now?
Yeah, yep, you're good.
Just gonna
Okay, good.
share. So I know I'm on my computer. I had to switch. My iPad was died.
Okay.
Just going to quickly switch over to the data report. Looks like everyone did a great job going through. Everyone's finding the space groups and the R values and the crystallization experiment. So I think we have a good feel for the PDB and where the necessary information is. So when they do their research, that shouldn't be a problem. The one thing I did want to show you real quick, because I know we're in a little bit of time, is this exercise is more about you going through the PDB web pages and finding the necessary information. But don't feel like you have to do that for each experiment or research you're doing. If you are doing, let's say, research, and let's say your teacher says, oh, we have MyOAB, you can click and search through MyAB. And this is a relatively new feature, I think, within the last 12 months. You can create your own custom reports. So when you're in the PDB page, if you look right here, it says what kind of report do you want. You can hit custom report and then bring up basically any information from all those pages that you want and get rid of all the information you don't need. So just let's say if you just want to know the ID numbers, and I've already clicked MyOAB, so they're just going to be all the MyOAB ID numbers. And you just want to do a quick search to see what ligands they're with. Or at the same time, you also want to know the space group. So you check those, and then you hit run report, and then basically what you'll get is just a quick list of all of the PDBs with their ligand and space group. And you see they all came up the same, and these are all the little ligands that are available. All right. And then if you're any good at using computers, you can download this as a CSV file, and then you can convert that to either a Google Sheet or an Excel sheet. So you could pretty much make the same thing that we did, but just specifically for all the targets that you have in your research. So if you're just trying to compare, let's go back and say, all right, Got a clear custom report. You got to hit modify the second time around. Let's say instead of ligands, I want to know where is it? Oh, it's up here, I think. Sorry, it's getting noisy in my house. There should be crystallization method. And then you hit run report, and then you'll have all the types of, you can make this bigger, all the conditions for those in section, only showing 25. So there you have all now the crystallization methods. And then if you dump this into a CSV, you can turn that into an Excel spreadsheet, and then you'll have every single condition for every single MyAB. And it'll give a quick glance. And actually, if you do that, you'll probably notice most of the conditions are the same because it's the same protein from the same species. But there may be some anomalies there. There may be with one ligand it worked better with others. All right?
Mm-hmm.
So that's all I have on that. So I will stop sharing. Any questions?
That girl that was just on blonde, she was in Charlie and the Chocolate Factory.
No?
No, I think they're good. Yeah, and again, that information is really important for us moving forward when we're looking at what types of conditions we want to use to crystallize proteins and what space groups are available out there. What was the resolution they had? Because a lot of times when we're collecting data at the beamline, the scientists will ask us, "So what resolution? Were these at? What space groups did they have in previous research?" And then we can just quickly go to the spreadsheet and say, "Yeah, we had the best resolution was 2.8 angstroms," or this space group was such and such. Or they may say, "What was reported with this ligand?" No, we never had anything with this ligand. This is the first time we're doing this. Or maybe we can say, "Yeah, we're doing this again, but we've come up with a different space group." So it really becomes a valuable tool to us as we're doing this. I want to switch up to just kind of wrap things up, but I know we're going to run over about 5 or 6 minutes, and Google is telling me that we only have a couple of minutes left. So I'm going to put right up here in the chat. This is another meet that we can just open up and go right to. So if everybody just clicks on that, that'll open up another meet, and you can just jump right on that. That's fine, Leda. Definitely. Thank you. Yep. You can call me when you're done with that meeting if you want. That'd be great. I'm available. Thank you. So everybody can just click on that meet, and then I'll jump right in with that, and we'll just wrap things up and let you guys know where you want to go next. Wow, that went smooth. Nice quick switch over. Okay, I think we have just about everybody on, right? Can you guys hear me? So give me a thumbs up that you can. Okay, good. Excellent. Just wait another minute. Make sure we have everybody. We have 29. Yep. Okay.
Is that why you watch the Minions? Because of those commercials? No. I thought that's why, because those commercials that went on with the Minions.
All right, so we're going to wrap things up. So, what's next? Okay, so this week we introduced you to what proteins are, what protein crystallography is about, how we get the proteins, how we crystallize proteins, how we freeze them, shoot them with X-rays, and do a little bit of work with the data so we can figure out what's what with the proteins. We also learned this morning from Bruce what the synchrotron is all about, that it's really a gigantic microscope that we use to visualize the proteins. Okay, so what's next? Okay, for the rest of this month into August, if you know of or you are interested in a disease or a disorder and you want to research that a little bit more, I would suggest you start doing a little Google search about that disease and disorder to determine if there's a protein that's related to it. For example, a few years back, we had students that were interested in Lyme's disease and tick-borne diseases, and they found out that there was a protein that was being studied, the tRNA methyltransferase, associated with anaplasmosis. They went to their teacher about that protein and said, hey, I think this might be something neat. And then the next step was to search for the protein in the PDB to see if it was even in there. If it is in the PDB, you want to maybe start making a Google Doc with some of the information about it. Do a search just like we had you do the other day with the data report on that protein. The next step you might want to do is look to see if we can get that protein from Seattle Structural, okay? And you can do that yourself. The link is here in the slide. These slides are going to be on the Google Classroom. So you can click right here and that'll take you right to the Seattle Center for Infectious Diseases. And you literally just type in the name of that protein and you can see if it comes up. The other important thing is to share any information you find with your teacher. Proteins that are available at Seattle, we can have them shipped to our houses. We can get them usually within a week or so, and we can store them in a freezer and then bring them over to the school in September. Just a couple of things to keep in mind as you're searching for proteins. Two things you got to be careful of. One is membrane-bound proteins. We can't work with them. They're very difficult to work with. The failure rate is extremely high with those. Even some experienced scientists that we tried working with about a year or two ago told us we don't want to go near that. It's just it's too time intensive and too labor intensive. The other thing is highly infectious proteins. If you're looking at a disease that's infectious, we have to be careful. So you find the protein, let your teacher know, and then we can ask Aleda to check with the lab to determine if that's something we can work with at the lab or even in our schools. Some of these are high level infectivity, and we have to be very careful about bringing stuff into the school. Okay. But that's the first step for July and August. So, and again, if you have that interest, get in contact with your teacher. Tell them you have an idea. Take a look at the PDB. If that protein's not in there, that might even be a better opportunity for us because it may not even be something that's published. Okay. In the fall, here's what's going to happen. You're going to get back to school in September. Perhaps you're going to find an idea about a protein, or your teacher's going to come to you and say, oh, hey, we have a protein that we're going to study. We're going to go to the PDB and we're going to start looking at those articles as a starting point. And your teachers are going to teach you how to set up a literature search where you're going to find, read, and review articles that are specific to that protein. Ultimately, what you're going to do is learn all the background information you possibly can about that protein. We're going to look at what types of conditions are used to grow it. What materials do we need to crystallize these proteins? We're going to look at, have these proteins been crystallized at all? If so, have they been crystallized with different compounds? What compounds haven't they used yet? So you're going to develop a cohesive literature review that basically will be sufficient enough to write an introduction about the prior research and the background on the protein that you and your teacher are going to be looking at. Further on into the fall, once we have that done, we're going to look at dates and times for setting up wet lab work and data collection. And this is all contingent upon Brookhaven lab access. Right now, we are crystallizing the proteins in our classrooms at school. If we can get access to the lab at some point, we're going to then try to do the crystallization at the lab because it's just easier to do it all in one spot. Right now, the plan is to remotely access the beam lines at the synchrotron, but if things change, we may be able to get some students at the experimental floor at the synchrotron. The other thing that's going to happen in the fall is all students are going to complete training and you're going to receive a Brookhaven National Lab appointment. What that basically means is that's going to give you access to their computer system and access to the lab. You'll hopefully get an actual badge with your picture, which is the same badge that any other scientist would have, and you would have a certain degree of access to the lab. Students sometimes have limited access compared to a full-fledged scientist. But that's all going to happen in the fall, and your teacher will contact you and let you know about that information. We do need to collect information from you, such as your name, your grade, email, and then you're going to receive emails from the lab about registering. But you'll become a registered user of BNL. And practice makes perfect. So before we even touch an experimental, hard to find, expensive protein, we're going to set everyone up with making practice trays using the enzyme lysozyme, which we can get anywhere, anytime. But you'll practice creating crystallization conditions. You'll change those conditions. You're going to grow crystals of lysozyme. You'll even practice with cryoloops. We have plenty of those. How to fish the crystals out of the trays and how to screen for the proteins. The other thing you're also going to learn is how to analyze diffraction data. We have some data files that you can use to learn how to utilize the program CCP4 and COOT. So a lot of that's going to be happening once school starts. And again, we're going to go through this in a very stepwise sequence so that everyone really gets a good understanding of how everything works. Okay. So that's kind of what's going to happen now after we're done with this introduction that you guys have all had. And teachers, do you have anything you want to add or chime into before we wrap things up?
I just want to ask my three girls if you guys can just get onto our team for the summer training, and after this meeting, I'll just start a chat. We don't need to video conference, but I just want to do a chat with all three of you to kind of outline how the rest of our summer is going to go.
Okay. Oh, and something just came up I think there was a question. Sounds good. Okay.
Yeah, no, that's my girl.
All right. Gotcha. Yeah. I think at some point, all of the teachers are going to be communicating with the students, whether, we're going to do it during the summer or closer to the beginning of the school year. But certainly I'm going to just put it out there to my students, my ESM students, reach out to me anytime during the summer. If you have an idea, if you have a question, I will be reaching out to you guys at some point. But once we start up in September, we'll get the ball rolling. We have some plans and ideas already. I spoke to you guys right before school ended. So we'll be going along with that. And I think that's it. That's what I have to say regarding, my students. So basically that's it. We want you guys to have a great summer and enjoy the rest of the summer. We've laid the foundation for what you need moving forward. You students will have access to this Google slide presentation and actually to the whole classroom throughout the school year. We're gonna keep this up and running. And again, if students have an interest in a particular disease or a protein, reach out to your teachers, because the best way to do this is if students have the interest. I mean, certainly I have some ideas for my students, but if you guys have something that you're interested in, we'd rather have it come from you and have you guys run with it, because that makes it much more interesting, and it makes it much more of a connection. So I want to thank.
Really,
go ahead. Yep.
Really quick, Esther asked about OSPC. It's in the chat.
Yeah. Oh, okay. I didn't see that. We're still going with OSPC. We're going to try to go with that. We're giving that a shot. Alex, we were waiting for Alex to come back. He was out of the country for a while. So he's back in, and what we're hoping to do is once things kind of settle down with his beam times and everything, to get him to work on that for us, Esther. So where we left off with that is we were waiting for him to run echo to do a screen to see if we could get any crystals. And if we have crystals, then the next step would be, okay, let's optimize it, and then we can try to get some beam time in the fall for that. So we're still going to try. We're giving this one last shot. If this set doesn't work with Echo, then I think we have to say that's it, because we're almost out of protein. So, but we're going to try one more time. So he has the protein. He just never ran the Echo for us. He was going to, and then he had to go out of the country for a couple of weeks and just got back not too long ago. Okay.
Okay.
You got it. Yep. We'll keep you. We're going to keep you in the loop. Don't worry. All right. So, anyone else? Any other questions? Okay. So, students, go ahead. Yep. Go for it.
Just a quick suggestion too, when you mentioned when you're looking, try not to, especially this early, try not to get married to just one protein.
Yeah.
You might, if you have an interest in disease, you might want to pick up a few, because which one's going to be available, which one's going to crystallize. So when you're first starting your research, try not to get down just to a single protein from a single species. Like I said with my group, Anna was the disease that we found in a tick from a barcode project. It took us a long time to find TRMD though.
Right.
So, we went through several proteins and it was just, no, start again. Nope, start again until you find that. So be prepared just to keep a bigger net when you're going through that.
Yeah, that's true. Yeah, you don't want to just zone in on one and then it winds up being a dead end.
Right.
So, right. Okay.
It was helpful that they liked the disease because I think their uncle had it. So
okay.
they kind of were really, at least they stayed persistent on.
Right. Yeah. And now we're on the verge of a publication on that, which is phenomenal. Thanks, John. All right.
Sure.
All right, students, it's been wonderful having all of you guys. This is a great way to start up, getting everybody up on the same page. So at this point in time, we're all on the same page. And so moving forward in the collaboration, whether we have schools that start working together or we have schools that are working, on different proteins by themselves, we're all in it together. And all the proteins belong to all of us. It's not just like, oh, these are only ESMs and this is only, Connect Quats. This is everyone's in it together. And so, as we move forward together, we're all going to be learning as we go through. So we all appreciate you taking the time out of your summer to be with us and to join us. It's 11:10, so we only went 10 minutes over on the last day, trying to, keep the timing to a minimum. So again, guys, students, have a great summer. Reach out to us during the summer if you have ideas. And in September, we'll be rocking and rolling and hit the ground running. So students, have a great summer. You guys can log off. Teachers will just stay on for like a minute just to debrief, and that's it. All right. Thanks, guys.
Dad, I know you said that we're gonna work with you, but are we picking our protein or are we not picking our protein?
I'll tell you guys after. Yeah.
Because me and my friends, we have some specific reasons.
Okay.